Our universe is an immense space with a scale far beyond human imagination. The number of stars in the universe is estimated to be greater than the number of grains of sand on all the beaches on Earth, combined, a number that is difficult for humanity's understanding to grasp. However, contrary to the impression of a crowded universe, the reality shows that the universe has an incredibly low density of matter. If each star were scaled down to the size of a grain of sand, the average distance between these grains would be around 8 kilometers, equivalent to the height of Mount Everest. When converted to actual scale, this distance corresponds to 5 light years, a distance that current human technology cannot overcome. To put this into perspective, NASA's Parker Solar Probe, fastest spacecraft ever built by humanity, would need about 7,000 years to travel from Earth to the nearest star. Notably, this is just the distance to one star. The nearest galaxy is hundreds of thousands of times farther away. Faced with such immense distances, humanity seems trapped in an invisible cage formed by the laws of physics, restricting all efforts to explore the universe. However, humanity has not given up hope. While science and technology have their limits, imagination does not. Based on a combination of physical theories and imagination, we can envision a spacecraft capable of taking humanity to the farthest reaches of the universe. This journey promises to be filled with countless wonders. What will happen when we travel aboard such a ship? And what awaits at the end of the universe? Prepare yourself for this adventure. Our imagined spacecraft is designed to far exceed what humanity can currently build. The ship has the ability to accelerate steadily at 10 m, an acceleration slightly higher than gravity, about 9.81 m/s, ensuring the safety of passengers. After 40 seconds from departure, the spacecraft's velocity reaches 400 m/s and continues to increase. We assume that this ship could accelerate indefinitely over long periods, something not yet possible but entirely imaginable in this scenario. In addition, the spacecraft is equipped with the ability to withstand all types of radiation and potential collisions during its journey. Inside the ship, thanks to an acceleration equivalent to Earth's gravity, passengers will not experience weightlessness as depicted in science fiction movies. Daily activities proceed as usual. Although the initial phase seems slow, the spacecraft's speed will quickly accumulate. After about 2.5 hours, the ship will have passed the Moon. After a day and a half, Mars will be left behind. Remarkably, just 3 weeks later, we will have exited the solar system, reaching a speed of more than 65 million kilometers, equivalent to 6% of the speed of light in a vacuum. However, this speed is still not enough for the effects of special relativity to become significant. This information is crucial for the next phase of the journey. Immediately after leaving the solar system, our next target is the nearest star to Earth in the universe, Alpha Centauri. If you wish to learn more, you should research this star system. The light from Alpha Centauri grows increasingly brighter, while the Sunday is now just a faint dot outside the window. Over the next year, there will be no major events, except that the spacecraft's speed will continue to increase each day. Currently, direct communication with friends and family on Earth is impossible due to the lengthy time it takes for radio waves to travel. However, the sense of loneliness is somewhat alleviated by the news updates covering current events, culture, sports, and scientific discovery 7, though they occasionally come with some delays. After 15 months from departure, our crew celebrates the milestone of surpassing the distance of 1 light year. This is an astonishing fact. As of now, we have covered a quarter of the distance to Alpha Centauri. In terms of time, we have completed a third of the journey as the spacecraft's speed continues to increase over time. Another significant milestone we've achieved is that the Lorentz factor of the spacecraft has now surpassed a value of 2. The Lorentz factor, according to Wikipedia, is a quantity used to describe the curvature of space-time, directly proportional to the speed of the object. The formula to calculate the Lorentz factor is gamma is 1 divided by the square root of 1 minus the square of the object's velocity, divided by the square of the speed of light. In this formula, J1, Ma3, gamma, is the Lorentz factor, v is the velocity of the object, and c is the speed of light in a vacuum. As the speed approaches the speed of light, the Lorentz factor increases, leading to the special effects described by Einstein's theory of special relativity. 1. Length contraction. From the perspective of an outside observer, the length of an object in the direction of its motion appears contracted. 2. Time dilation. Time inside the spacecraft passes slower compared to time for an observer on Earth. In this case, the time that has passed since the ship's departure, according to Earth's clock, is 15 months. However, the crew on board experiences less time due to time dilation. Currently, the spacecraft's speed has reached 87% of the speed of light. If the acceleration continues as it is, the observed speed will reach its maximum in the next 45 days. However, according to special relativity, no object can travel faster than the speed of light. Even though the spacecraft's speed approaches light speed, an outside observer will only see the maximum speed as the speed of light. To make this clearer, let's compare it to a car. If you are driving at 90 km per h and chasing another car moving at 100 km per h, you will observe that the other car is moving away from you at only 10 km per h. But when chasing a beam of light, its speed remains fixed at 300,000 km per s, regardless of how fast or slow you are moving. This phenomenon occurs because the speed of light is a constant, independent of the motion of the observer or the light source. Therefore, to maintain the constancy of the speed of light, time and space must adjust. This adjustment is expressed through the Lorentz factor, and is the reason why time and space on our spacecraft differ from those on Earth. An observer on Earth will perceive our journey as taking longer than what the crew on board experiences. This is a direct demonstration of the effects of special relativity on this interstellar journey. Additionally, when the Lorentz factor exceeds a value of 2, it begins to affect how the acceleration of the spacecraft is perceived from Earth's perspective. An observer on Earth will notice that the spacecraft is no longer accelerating at 1g, but its speed increases more slowly until it approaches the speed of light. Therefore, when we say nothing is faster than light, we are speaking from the perspective of an external observer. However, for you and the crew on board, everything proceeds as normal. The spacecraft continues to accelerate, and in fact, it has already exceeded the speed of light from the perspective of the crew. This becomes more apparent when you look outside the window. The Sunday's light quickly fades, as if we are being separated from the rest of space-time. However, infinite acceleration is not a feasible idea, as our energy source is not infinite. At some point, the spacecraft will need to decelerate to stop and land, which will also require an enormous amount of energy. We can calculate to decelerate the spacecraft with an acceleration of -1g, decreasing the speed by 10 m per s every second until it comes to a complete stop. To do this efficiently, the deceleration process will begin once the journey reaches halfway. Returning to the initial journey, the first destination is Alpha Centauri, which is 4.4 light-years away from Earth. A light beam from Earth takes 4.4 years to reach there, but aboard the spacecraft, only about 3.5 years will pass. This does not violate relativity because, from Earth's observation, the actual journey has lasted 6 years since the beginning. You will have a few weeks to explore Alpha Centauri before heading back. The return process is similar, accelerating with 1g until the halfway point, then decelerating with -1g. Upon returning to Earth, the total time for you will be about 7 years, but for people on Earth, the journey will have taken 12 years. This is an impressive duration for humanity to reach the nearest star. Another important detail is the timing of deceleration, which occurs 2.2 light-years from Earth, around 1.8 years after departure, according to the spacecraft's time. At that point, the spacecraft's speed reaches 95% of the speed of light. However, after reaching Alpha Centauri, a heated debate occurs among the crew members. Eventually, everyone decides not to land on Alpha Centauri but to continue the journey, using the spacecraft to explore further into the universe. The new journey is divided into 4 phases: acceleration on the way out, deceleration on the way out, acceleration on the way back, and deceleration on the way back. The next goal is to travel beyond a distance of 30 light-years to escape the boundary of the local interstellar cloud, the region where the solar system is located. To complete this journey, the total time on board the spacecraft will be 133.4 years, including both the outbound and return trips. However, upon returning to Earth, our descendants will be nearly 70 years old, leading to strange reunions like those in the movie Interstellar. After crossing the 30 light-year boundary, we will enter a region of space known as the local bubble, a structure that extends over 300 light-years. To complete the round trip through this region, the spacecraft will need an additional 22 years on board. However, when we return to Earth, 600 years will have passed. Faced with such vast distances and the passage of time, we may wonder whether those remaining on Earth will still remember that 600 years ago, a crew departed from the planet to explore the vast universe. 22 years aboard the spacecraft is no short time, but 600 years on Earth would bring a completely unfamiliar world with changes beyond our imagination. Although age will inevitably increase after such a long journey, the crew can continue to contribute to a further mission. A potential goal could be to leave the Orion arm of the Milky Way. With the spacecraft's continuous acceleration, a round-trip journey to the edge of the Orion arm and back would take only 41 years aboard. The journey would be divided into 4 phases: acceleration on the way out, deceleration on the way out, acceleration on the way back, and deceleration on the way back. The spacecraft reaches its maximum speed in the 8th year, completing the acceleration phase on the outbound trip. After about 6.5 years aboard, a strange phenomenon will appear outside the window. A region of bright red light gradually becomes visible. Initially, it may seem like an illusion or a visual issue, but in fact, this is due to the Lorentz factor reaching 650. The cosmic microwave background radiation is shifted into the visible red light spectrum, creating this unusual scene. As the spacecraft reaches maximum velocity, the space outside seems to glow red. It feels as though the spacecraft is attracting the attention of the universe itself. Beyond the edge of the Orion arm, the next goal could be the edge of the Milky Way, over 100,000 light-years from Earth. The round-trip journey would take 41 years aboard the spacecraft. When returning to Earth after this journey, the crew members will be over 60 years old, while on Earth, millions of years will have passed. After 1 million years, society and technology on Earth will have changed beyond our current imagination. Due to limited living space, large space stations in orbit may become an alternative. 3 potential models for future space stations include: 1. Spherical settlements, capable of generating artificial gravity suitable for populations ranging from 10,000 to 1 million people. 2. Torus settlements, large circular designs with living and agricultural areas. 3. O'Neill cylinder settlements, the largest design featuring large windows to let sunlight in, creating Earth-like landscapes. People would live on the curved surface and could grow crops there. Radiation will be blocked by polyethylene shields or electromagnetic fields, similar to how Earth's magnetic field protects us from cosmic rays. Technology supporting life in space includes: 1. Oxygen production. Technologies like water electrolysis and the conversion of CO into O are being developed to help sustain life on planets such as Mars. 2. Compact nuclear energy. Small-scale nuclear fuel cells 12 times 18 centimeters can provide long-term energy for space settlements or interstellar journeys. When humanity returns to Earth after millions of years, the world will have transformed in unimaginable ways. Technologies and off-planet settlements may have become the norm, allowing humanity to expand its living space and maintain long-term existence in the universe. NASA is utilizing 3D printing technology to develop lunar habitats, which are expected to be completed by 2040. The primary material for construction will be lunar dust, and these homes will be designed to be safe for human habitation. In 2022, NASA successfully conducted the Artemis 1 mission, the first test flight of the Artemis program aiming to return humans to the Moon. The spacecraft orbited the Moon and returned safely to Earth. 1. Artemis II, taking place in November 2024, will send 4 astronauts into lunar orbit on a 10-day mission. 2. Artemis III, initially planned for 2025, will be the mission that lands humans on the Moon's surface. However, due to some challenges, the schedule has been delayed. The Moon is not the final destination. According to NASA's plans, it will serve as a stopover for refueling on the way to Mars. NASA is currently testing Mars-like living conditions in Texas, USA. From June 2023, 4 volunteers have been part of a year-long simulation, acting as real astronauts. At the same time, Elon Musk's SpaceX has set its sights on sending humans directly to Mars for settlement. However, this remains a hypothesis, as the million-year journey of humanity carries countless unpredictable factors. The language of future Earth inhabitants may be radically different from what we know today. The spacecraft's journey log might become a valuable ancient document symbolizing a once thriving civilization from the past. Although the lifespan of the crew is limited around 60 years for some, with a few lucky members possibly living an additional 15 years, a 56-year journey would make it possible for humanity to undertake a round trip to the Andromeda Galaxy, the closest galaxy to the Milky Way. This journey would allow us to witness another galaxy firsthand, even if some crew members may not make it back. When returning to Earth after 5 million years, if humanity no longer exists, the planet may have undergone significant recovery. Nature will regain control, and biodiversity might return to a state reminiscent of Earth before humans. The crowded cities would disappear, replaced by vast forests and coral reefs stretching across the oceans. To undertake journeys beyond Andromeda, extending lifespan is essential. Scientists from the Mayo Clinic have developed a method to extend the lifespan of mice by 35% without causing significant side effects. If successfully applied to humans, the average lifespan could increase from 71 to 95 years. This technology works by removing old, weakened cells that no longer have the ability to divide. This helps delay age-related diseases such as cardiovascular disorders, kidney failure, and cataracts. Old, weakened cells appear throughout the body over time, from the skin and muscles to the internal organs. These cells function like an emergency brake to prevent further cell division, reducing the risk of cancer. However, when the number of these old cells increases too much, they become a burden on the body. When people are younger, the immune system regularly removes damaged cells from the body. However, over time, this function weakens, causing damaged cells to accumulate in organs, leading to significant harm. Notably, these cells are linked to dangerous conditions like heart failure, arthritis, Alzheimer's, and cancer. To address this issue, researchers conducted gene mutations on laboratory mice to stimulate them to continue producing caspase, an important protein that helps eliminate damaged cells. This protein is only activated to respond to p16 proteins produced by the old cells. The research process included adjusting caspase using a special drug. Middle-aged mice were injected twice a week throughout their lifetimes. The results showed that the lifespan of the mice was extended by 17 to 35%, and they remained healthier than untreated mice. However, this therapy is not yet perfect. Some old cells, especially those in the intestines and liver, have not been removed, leading to difficult-to-control damage. In the future, researchers aim to develop a method to completely remove aging cells in humans, which is much more challenging than in mice. Unity Biotechnology has invested in this research, hoping to develop a drug capable of eliminating 60 to 70% of the old cells in humans. If successful, lifespan-extending technology will no longer be a dream but a reality, paving the way for journeys beyond the Virgo cluster, where humanity currently resides. The Virgo cluster is located within the Laniakea supercluster, a vast region of space stretching across millions of light-years, containing tens of thousands of galaxies. A round trip beyond this galaxy cluster would take about 76 years at the spacecraft's maximum speed. During the journey, the Lorentz factor would reach 250 million. Upon returning to Earth, the time difference between the spacecraft and the home planet could make it unrecognizable. Continents would have shifted from their original positions, plants and animals would have vanished, the air would become unbreathable, and Earth would be left with only traces of a once thriving world. The Sunday's brightness would increase by nearly 10%, accelerating the weathering process to a severe level. The reduction in CO would prevent plants from photosynthesizing, leading to the complete collapse of the ecological chain. If fortunate, we might find a few simple microorganisms still alive. In this return, humanity would surely feel sorrow upon witnessing Earth, once a vibrant home, now a planet slowly running out of life. To forget the grief of returning to Earth? Another option would be to never return. Laniakea is not the edge of the universe, and we could travel further. Thanks to time dilation, we could journey even farther at an exponential rate year by year, using a spacecraft that achieves 1g acceleration. However, can humans reach the edge of the observable universe? Sadly, the answer is no. The vast distances of billions of light-years, combined with the ever-increasing expansion of the universe, make it an insurmountable challenge. In 1998, astronomers used telescopes to observe distant supernovae and study the expansion rate of the universe. They discovered that not only is the universe expanding, but it is also accelerating. This phenomenon, believed to be caused by dark energy, causes the distance between regions of space to grow increasingly larger. Based on measurements, the farthest distance light has traveled since the Big Bang, 13.8 billion years ago, is approximately 133.8 billion light-years. However, due to the expansion, this distance is actually 46 billion light-years. When we exit the gravitational pull of the superclusters, our spacecraft would be directly affected by the expansion of the universe. This would make the journey progressively more difficult. Scientists have calculated that the furthest boundary humanity could reach if they still wish to return us about 8.3 billion light-years. If we surpass this boundary, we would be trapped in the void forever, as the expansion rate of the universe is much greater than the speed of light. If this is a one-way journey, what will await humanity beyond the 8.3 billion light-year boundary? The current answer is nothing. As we continue to accelerate over the course of 200 years, time on Earth would have passed 10 circumflex 41 years. This is enough time for even protons, in theory, to completely disappear. Thus, our journey would end at the farthest point where there is neither time nor space. But even here, no conclusions are ever final because science is constantly evolving. A few centuries ago, humanity believed the Earth was flat and the center of the universe. But now, science has opened up boundaries we never imagined. Who knows? With a few scientific breakthroughs, the universe may no longer be as mysterious in the future. The question arises, if all ultimately leads to nothingness, is exploring the universe still meaningful? Perhaps this is something to leave to scientists, those who truly understand their goals. Whether humanity achieves its dream of space exploration as we know it today or not, one thing is certain: human ambition will always drive civilization further.